Good morning, students. Myself, Vijay Shankar from BC Department, Chevrolet Engineering College. Today, we are going to discuss about the uniform plane wave in perfect dielectric, practical dielectric, and good conductor, lossy dielectric. In yesterday's class, we completed the lossless dielectric, uniform plane wave in lossless dielectric. Now you can see the lossy dielectric, uniform plane wave in lossy dielectric. See, before going to the uniform plane wave, the lossy dielectric, recall some formulas regarding these functions. The gamma is equal to, we know the alpha plus I beta is a phase constant, attenuation constant, and the combination, the phase constant is a imaginary coefficient and attenuation constant is a real term. The propagation constant gamma is equal to under root of j omega mu whole multiplied with the sigma plus j omega epsilon. The propagation constant eta is equal to, it is under root of j omega mu by sigma plus j omega epsilon. The lossless dielectric means already we know the lossless dielectric means alpha is equal to 0. Lossless is a conductivity is a 0 there. When conductivity is 0, gamma is equal to, it becomes of under root of j omega whole square. Since the sigma is equal to 0, mu into epsilon. Mu into epsilon. So bring that in the outside of j omega under root of mu epsilon, having only the imaginary coefficient. So alpha is equal to 0, beta is equal to, you get the omega under root of mu epsilon. Similarly, in this, the conductivity is a 0 in the lossless. Conductivity is a 0. The eta is equal to under root of j omega mu by 0 plus j omega epsilon. Means mu by the epsilon. Okay, now we can go for deriving the expression for the uniform plane wave in the lossy dielectric. Lossy dielectric means the alpha is not equal to the 0. Understood, my dear students? Listen carefully. Practically, all the dielectric materials exhibit some conductivity. In the previous case, in the lossless, we take the conductivity as a 0. But practically, all the dielectric materials exhibit some conductivity. It's not ignorable. So we cannot be directly neglect the sigma, assuming it is a 0. The results obtained for perfect dielectric medium, the results for lossy dielectric will be different. Here alpha is not equal to the 0 in a practical condition. So the gamma, the propagation constant alpha is equal to under root of sigma plus j omega epsilon into j omega mu. Okay, my dear students. So in the previous case, I 0, the conductivity is a 0. Then alpha becomes a 0. Now it is not, alpha is not equal to the 0 because for every dielectric materials, practically there exhibits some conductivity which is not directly neglect or assuming to the 0. Okay. So gamma is equal to, now if I am taking that j omega mu sigma plus j omega epsilon, in the parentheses we can take the common then it becomes of 1 plus j omega epsilon. Got it, matters. So when I'm taking in this parenthesis, j omega epsilon is a constant, we'll get the 1 and sigma by this one get cancelled, sigma 1. That is equal to, you can write this as a j omega into j omega is a j omega whole square. Write in the outside j omega and epsilon mu epsilon and another under root of 1 plus sigma by j omega epsilon. Okay. And this the gamma is nothing but alpha plus I beta. From the equation, it is clearly that the propagation constant for lossy dielectric medium is different than that of the lossless dielectric medium. Radial factor becomes unity. The radial factor means whenever if it is a perfect dielectric and it is a lossless, and we can obtain the propagation constant gamma for a perfect dielectric. It is also clear from the equation 2 here. The attenuation constant alpha is not the zero. Attenuation constant alpha is not the zero. But substituting the values of omega, sigma, mu, and epsilon, the attenuation constant alpha and the phase constant beta may be calculated. Okay. The presence of alpha indicates a certain loss of signal. If alpha is not the zero means definitely there is a loss is occurs, then we can call it as a lossy dielectric one. The presence of alpha indicates certain loss of signal in the medium. Hence, such medium is called lossy dielectric. The lossy dielectric. When a wave propagates in a lossy dielectric, the amplitude of signal decays exponentially due to the factor of e power minus alpha into z. For the forward as well as a backward wave, so the amplitude decays exponentially whenever if it is in the lossy dielectric. And as the sigma is not the zero, the intrinsic impedance also becomes a complex quantity. It's given by the eta is equal to j omega mu by the sigma j omega epsilon. We have the eta is equal to j omega mu by, you can take the denominator also, the j omega epsilon, you can take the common 1 plus sigma by j omega epsilon. Again, so j omega get cancelled. And here the another radial factor. The radial factor is 1 plus sigma plus j omega epsilon. It depends upon the sigma by omega epsilon is less than 1 and the greater than 1, depends upon the condition. We can take it is a perfect dielectric or the lossy dielectric. Okay, being a complex quantity, eta is expressed in the polar form as shown in the equation. This angle theta n indicates the phase difference between electric and the magnetic fields. Thus, in lossy dielectric, the electric and magnetic fields are not in time phase. In the lossless dielectric, we say that the E bar and the H bar, electric and the magnetic fields are in phase. But in the lossless, not the lossless, lossy, in the lossy dielectric, E bar and H bar are not in time phase. Okay, got it, my friends? So the eta is equal to, that is j omega mu sigma plus j omega epsilon. Take the j omega epsilon. The radial factor we got 1 plus sigma by j omega epsilon. Got it? So under root of mu by epsilon and this total factor we can write as theta n is equal to, is given by the theta n is equal to 1 by 2 pi by 2 minus tan inverse omega epsilon by the sigma. Omega epsilon by the sigma. It is subtracting from the by. This angle depends upon the properties of the lossy dielectric medium as well as the frequency of the signal. For the low frequency signal, the omega becomes very small. Then the theta n is equal to pi by 4. Is equal to pi by 4. The imaginary coefficient by the actually this imaginary coefficient is in the denominator, my students. The denominator means you can subtract from the pi by 2 minus. Okay. Why it is a pi by 2 minus means let us take the under root of j omega, the term is there. That is a 90 degrees minus the imaginary complex function. The complex function angle is tan inverse omega epsilon by the sigma. Okay, this angle depends upon the properties of the lossy dielectric medium as well as the frequency signal. For low frequency signal, the omega becomes very small. The theta is approximately equal to the pi by 4. For very high frequencies, the theta is approximately equal to the 0. Thus, the range of the theta and complete frequency range is from 0 to very high frequency is from the between of 0 to pi by 4. Okay. The next one is the uniform plane wave in the practical dielectric. It's a practical dielectric. We discussed the uniform plane wave in free space, uniform plane wave in a lossless dielectric or perfect dielectric, and uniform plane wave in the lossy dielectric. There is a radial factor. We have the under root of 1 plus sigma by j omega epsilon, and there is an angle having it varies in between of the 0 to pi by 4. So 45 degrees. Okay. And now we can go for the uniform plane wave in the practical dielectric. Okay. As we already studied, the perfect dielectric conductivity is a 0, but practical dielectric, the conductivity is not the 0, but it is very small. The condition for practical dielectric is that loss in the signal is very small. Practical dielectric, the loss is very small. You see, we are saying that it is a conductivity is not the 0 means that is not a lossless dielectric, lossless transmission and lossy transmission. That loss is also the very small in the practical dielectric. The loss in the signal is very small. That is, a sigma is very much less than the j omega epsilon. Let us consider the propagation constant gamma is equal to under root of j omega mu sigma plus j omega epsilon. Take the common again here, the j omega epsilon under root of j omega mu and j omega epsilon whole multiplied with 1 plus sigma by j omega epsilon. That is equal to j omega is a j omega square. You get outside the j omega under root of mu epsilon, and here another term is there, that is 1 plus sigma by j omega epsilon whole power 1 by 2. Okay, and this radial factor, whatever we have, apply the binomial theorem for this function as considered as a 1 plus x whole power n, where x is a sigma by j omega epsilon, n is equal to 1 by 2. That is equal to 1 plus n into x plus n into n minus 1 by 2 factorial x square and so on. Okay, and here also the 1 factorial is there by 1 factor. Neglecting the higher order terms, we can write this function as gamma is equal to j omega under root of mu epsilon, and for this function you can apply the binomial theorem, and by neglecting the higher order terms, 1 plus, what is the n here, 1 by 2, and what is the x here, sigma by j omega epsilon, sigma by j omega epsilon. Okay, so simplify the expression here. See the j omega under root of omega epsilon, 1 plus sigma by j omega epsilon whole power 1 by 2 can write as 1 plus 1 by 2 sigma by j omega epsilon. So see here, the gamma is equal to j omega mu under root of mu epsilon whole multiplied with 1 plus sigma by j into 2 omega epsilon, where gamma is alpha plus I beta, where gamma is alpha plus I beta or the j beta, multiply the term here, j omega with this function and j omega with this function, j get cancelled. We'll get as alpha is equal to under root of mu epsilon, j omega get cancelled. Sigma is in the numerator, and in the denominator we have 2 epsilon. Okay, this is for alpha only. Alpha is equal to. Okay, otherwise I will write all the equations. Multiply the term here, the gamma is equal to, first of all, the j omega under root of mu epsilon plus, multiply here the j omega get cancelled, under root of mu epsilon into sigma whole divided by the 2 into epsilon. So gamma is equal to, we know the alpha plus I beta, where alpha is a real term and the beta is an imaginary term. So j imaginary term, the beta is equal to omega into root of mu epsilon, and alpha is equal to, here the epsilon is a root is there, under here the root also epsilon is there. So you'll get 1/2 into under root of mu epsilon into sigma. Okay, the alpha and the beta values. So alpha is equal to sigma by 2 under root of mu epsilon, Napier per meter. Beta is the radius per meter, omega under root of mu and epsilon. Okay, the similar way for the practical dielectric, we can find out the intrinsic impedance also. What is the intrinsic impedance? Eta is equal to under root of j omega mu by sigma plus j omega epsilon. For this also you can take the common of j omega mu by j omega epsilon and whole multiply 1 plus sigma by j omega epsilon. So you get cancel of j omega and becomes of under root of mu by epsilon and 1 by 1 plus sigma by j omega epsilon whole power 1/2. This is eta is equal to. Got it, my dear students? Eta is equal to, I will written as the same thing. The 1 plus sigma by j omega epsilon in the denominator. Here they wrote it is a -2. Again, you can use binomial theorem. Binomial theorem to find out the eta is equal to, for practical dielectric, mu epsilon into 1 plus sigma by j omega epsilon is also there, my dear students. Epsilon whole power -1/2. Whole power -1/2 is 1 plus x whole power minus n is 1 minus n into x, n into n minus 1/2 factorial n square minus 1. So here also neglecting the higher order terms, the eta becomes under root of mu epsilon whole multiply 1 minus 1 is a 1 minus nx. 1 minus n is 1/2. X is a sigma by j omega epsilon. So the remaining higher order terms you can neglect. The n into n minus 1, n into n minus 1, n minus 2 by 3 factorial. Okay, so it is approximately. So n eta is equal to under root of mu by epsilon minus multiply here 1/2 into under root of here the epsilon here and the term the epsilon is also there, under root of mu epsilon into sigma j omega epsilon. The eta is equal. After substituting the value, the binomial theorem in that equation, so n plus 1 plus x whole power minus n is equal to 1 minus n into x, negating the higher order terms. You get the eta is equal under root of mu epsilon 1 minus 1 by 2 sigma by j omega epsilon. Got it, my students? Sigma by j omega epsilon. Understood? Using the above result, the intrinsic impedance can be written as, for practical dielectric material, the conductivity is very small. This indicates that the loss in the signal is also very small. Let us obtain the condition for indicates whether the loss is small or not. So we are saying that in the practical dielectric that the conductivity is there, that is very small conductivity. In the lossless transmission, we consider as a 0. In the lossy dielectric, it is not at all equal to the 0, assuming that. And that conductivity is a very small, means the loss is also very small in the practical dielectric. Loss in the signal is also very small. Now let us obtain the condition which indicates whether the loss is small or not. The Maxwell's equation, we know del cross H bar is equal to JC plus JD, where JD is a dou D bar by dou T, and D bar is a epsilon into E bar. Okay, and I already told that it is a replacing of J omega by the dou by dou T. So del cross H bar is equal to sigma into E bar plus J omega into epsilon into E bar. So sigma plus J omega epsilon into E bar. Okay, and del cross H bar is equal to JC bar plus JD bar. We know this one. This, the ratio of conduction current density and the displacement current density JC bar and JD bar is a sigma by J omega epsilon. These two current density vectors point in the same direction in a space as shown in the figure here. From the expression of a ratio of two current densities, it is clear that the displacement current density leads conduction current density by 90 degrees. So JC and the JD is 90 degrees. The angle theta by which the displacement current density leads the total current density is given by the theta is equal to tan inverse sigma by omega epsilon. Tan inverse sigma by omega epsilon. The tan theta is equal to sigma by omega epsilon. Okay, where sigma is very much greater than omega epsilon, the loss in the tangent is very high. Thus, the medium is said to be the good conductor. When the sigma is very much less than the omega epsilon, the loss tangent is very small. Thus, the medium is said to be the good dielectric. See, the sigma is very much less than means conductivity is a very small comparing to the dielectric, and it is also the loss tangent is also the small. Hence, any medium behaves a good conductor at low frequency, which exhibits the properties in the lossy dielectric at high frequencies. Okay, my dear students. Now we go for the another one, the wave uniform plane wave in the good conductor. Good conductor means conductivity is a more. Conductivity is a more means the sigma by omega epsilon is very much greater than the 1. So sigma is very much greater than the omega epsilon. So here you can neglect the omega epsilon. Okay, because we are selecting the uniform plane wave in the good conductor. A practical or good conductor is a material which is very high conductivity. Conductivity is a more. In general, the conductivity is of order of 10 power minus ohms per meter is a good conductor like copper, aluminum, etc. So it's very much greater than 1. The propagation constant gamma is equal to, we know the sigma j omega mu into sigma plus j omega epsilon. Okay. So as is a good conductor, the conductivity is very high. Gamma is equal to under root of j omega mu. Neglecting the term of j omega epsilon, we have only the sigma. So gamma is equal to under root of j omega mu sigma. That is equal to, I am writing as j under root of omega mu sigma. What is the under root of j? J is nothing but the converting this function into the polar form. The polar form, the magnitude is a 1 with an angle of 90 degrees with an angle of 90 degrees. Y means it is under root of. Y means 0 plus j is nothing but 1. Got it, my students? So what is the magnitude? The complex function magnitude is under root of 0 square plus 1 square. 0 square, 1 square means the value is a 1. So magnitude is a 1. I'm converting the rectangular form to the polar form and under root value. And what is the phase? Tan inverse y by x. Tan inverse imaginary coefficient is a 1. Real coefficient is a 0. 1 by 0 is infinite. So tan inverse infinite is nothing but pi by 2, 90 degrees. So inside the rectangular function under root j becomes of polar form 1 with an angle of 90 degrees. That 1 with 90 degrees under root is becomes of under root of 1 is 1 only. Angle of 90 degrees under root is a 45 degrees. Got it, my dear students? So the gamma is you can write as under root of j as 1 with an angle of 45 degrees. Why it is a 45 degrees, my dear students? Under root of angle 90 degrees becomes 90 by 2. 45 degrees. And under root of omega mu sigma. So we got the gamma is equal to, after substituting the conductivity is a more, gamma is equal to 1 with an angle of 45 degrees under root of omega mu sigma. 1 with an angle of 45 degrees, you can write it in the rectangular form as cos 45 degrees plus sin 45 degrees. Okay, cos 45 degrees plus sin 45 degrees. So simply you can say the magnitude is cos 45 plus sin 45. 1 by root 2 plus 1 by root 2 whole square. 1 by 2 plus 1 by 2 is a 1. Under root of 1 is a 1 more. And angle is sin by cos is a tan 45 degrees. And get it is a polar form is in the rectangular form. Sin 45 degrees and cos 45 degrees under root of omega mu sigma. What is the cos 45 degrees? 1 by root 2 plus j is also, my dear students, j into sin 45 degrees is also 1 by root 2 whole multiply under root of omega mu sigma. Multiply this under root of omega mu sigma in the two functions, two terms, and total under root of omega mu sigma by 2 plus j into under root of omega mu sigma by 2. So gamma is equal. What is the gamma? Nothing but alpha plus I beta. Alpha plus I beta. Here the alpha term is the same and the beta is also same. Therefore, in a uniform plane wave, the good conductor, the attenuation constant omega mu sigma by 2 is also equal to the phase constant beta. Alpha is equal to beta in good conductor. And gamma is sigma is very much high. And similarly, the intrinsic impedance eta is equal. What is the eta is equal to? Under root of j omega mu by sigma plus j omega epsilon. What we are saying, the conductivity is a very much greater than the dielectric. We are neglecting the j omega epsilon here. Approximately equal to under root of j omega mu by the sigma. Again, you can write this as under root of j under root of omega mu sigma. What is under root of j? Cos 45 and the sin 45 or 1 with an angle of 45 degrees. So cos 45, 1 by root 2 plus j into 1 by root 2 whole multiplying with under root of omega mu sigma. Okay, that is equal to eta is equal to, we got under root of omega mu by 2 sigma. 2 into sigma plus j into under root of omega mu by 2 sigma. So we got that eta is equal to gamma is equal to attenuation constant, omega mu sigma by 2, and here the eta is equal to omega mu by 2 into sigma. Okay. For the good conductor, we got the equations of phase constant. In that phase constant, attenuation constant, not the phase constant, sorry. Propagation constant. In that propagation constant, attenuation constant and phase constant is both are the equal. That is omega mu by 2. And the eta is equal to omega mu by 2 sigma. Got it, my dear friends? So let us see that the equations what we got here. So one with an angle of 90 degrees is the J. So alpha and the beta is both are the same. Omega mu sigma 1 by root 2 plus J into 1 by root 2. Why here? It is pi f into sigma. They are showing that pi f, we got the omega is equal to under root of omega mu sigma by 2 plus J into omega mu sigma by 2. They modified this under root of 2 pi f as a omega mu into sigma by 2 plus the J into under root of omega is nothing but 2 pi f mu into sigma by 2. So 2 to get cancelled. Here also 2 to get cancelled. What is alpha now? Alpha plus I beta is equal to under root of pi f mu sigma plus under root of pi f mu sigma J. So both alpha and the beta is the same here. Pi f mu into sigma. Therefore, for the good conductor, alpha is equal to under root of pi f mu Napier per meter. Beta is also same, pi f mu sigma radians per meter. Similarly, the intrinsic impedance for good conductor, alpha and beta are equal, and both are directly proportional to the square root of the frequency and conductivity. The intrinsic impedance for the good conductor is of a good conductor is given by eta is equal to under root of j omega mu sigma plus j omega epsilon. I already told the one angle with 90 degrees is one angle with 45 degrees. Write this here. Omega mu by, we got the intrinsic impedance is equal to actually omega mu by the 2 into sigma plus j into omega mu by 2 into sigma. His total is under root. Okay, my dear friends, that is equal. We can change this in terms of the normal frequency. The 2 pi f into mu by the 2 sigma plus j into 2 pi f mu by 2 sigma. The 2 get cancelled. Here also 2 get cancelled. Then it becomes eta is equal to under root of pi f mu by sigma plus j into pi f mu by the sigma. The intrinsic impedance eta is equal to. You see here, multiply this total factor with 1 under root of pi f mu by sigma plus j into, you can multiply with 1 pi f mu by sigma. Okay. Listen here. The angle of intrinsic impedance is a 45 degrees, as we already studied that for the perfect dielectric, that is a zero conductivity. The intrinsic impedance angle is 0, and for the good conductor, the angle is 45 degrees. Moreover, the intrinsic impedance has only the positive angle. It is clear that indicates the field H bar may lag the field E bar by at most the 45 degrees. By at most the 45 degrees. So consider only the component of electric field Ex traveling in the positive Z direction. When it travels in a good conductor, the conductivity is very high and attenuation constant is also high. Thus, we can write it as such component in the phasor form Ex is equal. The electric field traveling in the positive z direction. The amplitude we can consider as EM plus e power minus gamma into z, the positive z direction. What is the gamma, my dear students? Alpha plus I beta. EM plus e power minus of alpha plus I beta into z. Got it? That the equation becomes Ex is equal to Em plus e power, write the alpha minus alpha into z, and the beta e power minus j into or I into beta into z. This is a term we got. Consider only the component of electric field Ex traveling in the positive z direction. When it travels in a good conductor, the conductivity is very high and the attenuation alpha is also very high. Thus, we can written as the phasor form as Ex is equal to Em plus e power minus alpha into z into e power minus beta into z. Okay. Then when such a wave propagates in a good conductor, there is a large attenuation of amplitude as shown in the figure. It decreases here and it travels z is equal to t. When it travels z is equal to t, because the Ex is traveling in a positive z direction, it starts from the 0 and travel at the z is equal to t. Em into e power minus alpha z is becomes Em into e power minus alpha into z is a d distance. Okay. In the Ex, the amplitude is becomes Em and e power minus the attenuation. There is a large attenuation, the amplitude e power minus alpha into after the traveling of the d distance. At z is equal to 0, the amplitude of the component Ex is Em. Let us see here, Em. While at z is equal to t, the amplitude is Em into e power minus alpha into t. Why it is Em into, actually it is Em into e power minus alpha into z only. But z is equal to 0 means e power 0 is a value is 1 only. Then it becomes of Em. Now after traveling with z is equal to t, it becomes of Em into e power minus alpha into t. In the distance z is equal to t, the amplitude gets reduced by a factor of e power minus alpha into t. It reduces the factor e power minus alpha into t. If you select d is equal to, now if I am assuming that Em e power minus alpha, the d distance in terms of the alpha, if we can take alpha get cancelled, Em into e power minus 1. Okay. Then the factor becomes e power minus 1. The value is 0.368. So over a distance d is equal to 1 by alpha, the amplitude of wave decreases approximately 37% of its original value. You can take the 0.368 means in the percentage it becomes of 36.8. Is approximately equal to the 37%. So how much it is decreases from the actual value? The actual value is Em. It reduces up to the 37% of its original value when it travels d distance from z is equal to 0 to the z is equal to d. Got it, my dear friends? So over a distance d is equal to 1 by alpha, the amplitude of the wave decreases approximately 37% of its original value. The distance through which the amplitude of traveling the wave decreases to 30% of original value is called skin depth. That name we can call it as a skin depth or depth of penetration, and it is denoted by the delta. It is denoted by the delta. Remember, my dear students, when the signal is traveled in a positive z direction, its amplitude at the z is equal to 0 is Em. When it is after traveling the z is equal to d distances, it reduces its amplitude And that distance d is equal to, we can consider as a 1 by alpha. E power minus 1 becomes 36.368. Means for the original value, it decreases the amplitude as a 37% of it traveling in the d distances. Still, it is traveling in the more than the d distances. It decreases its amplitude, goes on the 0. That we can call it as a skin depth or depth of the penetration delta. That is equal to 1 by alpha or 1 by beta. Both are same because alpha and beta is both are the same in the good conductor. That is equal to 1 by under root of, we got pi f mu into sigma. This is the value of pi f mu into sigma meters. Skin depth means depth of the penetration. Delta is equal to 1 by alpha, that is equal to 1 by beta, that is equal to 1 by under root of pi f mu into, that is in terms of the meters. Okay. And the relation between of skin depth and the intrinsic impedance also we have, that we'll discuss. From the expression of the skin depth, it is clear that the delta is inversely proportional to the square of the frequency. Square root of the frequency, under root of f. Mu is constant, conductivity is also constant. So for the frequencies in microwave range, the skin depth or depth of penetration is very small for good conductors. And all the fields and currents may be considered as confined a very thin layer near the surface of the conductor. This thin layer is nothing but a skin of a conductor, hence this effect is called skin effect. The exponential decay of amplitudes of E bar or H bar component entering in the good conductor as shown in the figure below. See the EM and the HM, the surface of the good conductor, a thin surface, its amplitude is EM, and after it is traveled, the depth of the penetration after traveling with some distances, it reduces its amplitude is 0.37, nothing but 37% of its original value, and still it is goes on decreases when it is traveled more than the distance, exponentially decaying the amplitude of the field of the component of E bar with the distance along the positive Z direction. Okay, from the above plot, it is clear that 1 delta distance amplitude reaches 37% of its original value. For a good conductor, amplitude reduces to almost 0 within the 2 delta or 3 delta distance. Still, it is moving to the 2 delta or 3 delta, it almost goes to the 0. Thus, the uniform plane wave cannot travel the long distances through the good conductor. This is a final conclusion, my students. It's a very, very important point. Thus, the uniform plane wave cannot travel large distances through good conductor. This concept is used in the shielding of conductor. In a coaxial cable, the inner conductor carries a signal with the outer conductor carries a shield, which is made up of a material having the properties of the good conductor. So, even if there is an external interface, its amplitude is it goes to the reduced to the 0 within the very short distance due to the outer conductor, as the signal carried by the inner conductor is not interfaced by the external interface. See, what is the point we have to know here? After the discussion of a uniform plane wave in a good conductor, the skin depth delta is inversely proportional to the attenuation or the phase constant is nothing but directly proportional to the square of the inversely proportional to the square of the frequency. Means in the uniform plane wave cannot travel the long distance to the good conductor. Got it, Madam?